Okay, so let's proceed with part 2 for chapter 2 related to the general energy equation. Okay, as I mentioned before, for part 2 we are focusing on to how can we apply the general equation about the addition of energy or the loss of energy in a practical problems. Okay, so first of all, I will show you how can the equation of the general energy equation being derived. Okay, so basically the equation for general energy equation is derived by the extension or the expansion of the Bernoulli equation. Okay, so for example, in this case, if you look at the diagram here, okay, we have point 1 here in which that we want to transfer the fluid from point 1, okay, to point 2. Okay, so all the way from point 1 to point 2, there's a loss of device or unit or a condition in which that may lead to the addition of energy or losses of energy and removal of energy. Okay, so for example, okay, at point 1, okay, actually at this point, okay, the energy consists here is actually can be derived from Bernoulli equation. Okay, this is the normal Bernoulli equation for point 1. Okay, due to the potential energy, kinetic energy, and the total head loss. Okay, similar to this one, we also have the Bernoulli equation at point 2. So all the way from point 1 to point 2, okay, it may experience the addition or the removal of energy and the loss of energy. Okay, so let's take a look. Okay, the first one is go through a pump here. So we know that before a pump, okay, may lead to the addition of energy inside fluid. Okay, and it also goes through a valve and connecting devices or fitting here. Okay, 1, 2, 3. Okay, which is lead to the losses of energy. Okay, and then it also go through a motor here in which that at this point the energy being removed from the fluid. Okay, and then after that it continues until it reach point number 2. Therefore from E1, okay, and it goes through some HA, some HL, and the HR, then it will reach to the E2. Okay, so that's why the equation for the general energy equation is actually the E1 here. Okay, the actual energy which is processed by the liquid at point 1. Okay, and then we consider the addition of the energy due to the pump. Okay, and then we consider the loss of energy and the removal of energy. That's why this here is HR and HL. Okay, as you can see here, HL due to fitting and loss of the energy inside fitting or valve. Okay, and the removal of energy due to the motor here. Then it will reach point 2. Okay, I'll show you again how can the equation of general equation being derived, okay, step by step, because just now I just show you just like in general. Okay, so as you know that, okay, from point 1 to point 2, there's actually the addition of another energy. Okay, so in order for the liquid to achieve to change the to force the energy from E1 to E2, okay, it must go through another loss of energy and addition of energy. So that's why the equation being rewrite like this. If you see, remember in Bernoulli equation we directly equate between E1 is equals to E2. This is for Bernoulli. Okay, but for general equation of energy, okay, we add another these three term, which is the addition of energy, and the removal of energy and the loss of energy, then it will become E2. So since that we know that the energy processed by the system is this term, okay? So if we rewrite the equation at different point, which is at the point 1 and at point 2, so there we go, we will have the general energy equation. Okay, let's try this example. Okay, so for example, in this question, it mentioned that the water flows from a large reservoir. So this is the large reservoir. Okay, at the rate of 1.2 feet to the power of cube per second through a pipe system as shown in figure below. Okay, that's mean the water flow here at the rate of 1.2 is actually from here. This is where it is called a pipe. Okay. So this is as a Q2, which is the value is actually 1.2 feet cube per second. Okay. And then calculate the total amount of energy lost from the system because of the valve, elbow, and the pipe entrance. Okay. So as you can see here, okay, all the way down from the liquid at point 1, okay, to reach point 2, it may experience the loss of energy, okay, due to the valve. This is valve, and due to the elbow here, the connection, and the entrance of pipe and the fluid friction. So along this way, it may experience whether the addition or loss of energy, but it clearly shows that it didn't have any addition of energy or removal of energy. It just may experience the HL. Okay, so the question asks you to calculate what is the HL experienced by the fluid when it wants to move from point 1 to point 2. Okay, so we already have the info, so let's check it out. How can we solve this problem? Okay, as usual, the first thing that you should do when you get the question is you have to extract the information given in the question. Okay, so I already mentioned in the slide before that we have two different points, point 1 and point 2. Okay, so in order for the fluid to reach point 2, it may experience the loss of energy uh, due to the HL. Okay. Okay, let's take a look at point 1. So the information given from point 1, okay, it's not much given here, okay, but we can see that the distance here is given. Okay, so since like the point 1 is higher than point 2, so we know that Z1 minus Z2 is equals to 25. Okay, and then the information about the flow rate. Okay, the flow rate. Okay, here the Q2 is given, which is equals to 1.2 feet cube per second. Okay, and any other information? Okay, I think that's it. Okay, except that it is given us about the diameter for each location. Okay, so since that we know that we have to find the HL. Okay, so in this case, if you remember that, okay, the trick is from energy that posed at point 1, and then it consider when it is plus with the another energy loss or addition energy such as HA minus HL minus HR, then it will become E2. Okay, but in this case we don't have the HA and we also don't have the HR, so we only have the HL. Okay, so our equation will look like this: E1 minus HL equals to E2. Okay, so in this case we want to get what will be our E2. Okay, so if we can simplify this equation, okay, our HL is actually E1 minus E2. Okay, and we know that this is the general equation for the general equation of energy. So since I mentioned before here, okay, from here we know that it consists only HL. Okay, so therefore this item is cancelled out. This item also cancelled out. Okay, let's take a look at another item. Okay, for example, P1. Okay, so the pressure at point 1 here, okay, we consider it as 0 because it is exposed to atmosphere. Okay, the pressure here P1 will be equals to 0 because it is exposed to atmosphere. Okay, and then the velocity here V here we can also consider as 0 due to the huge free surface area. Okay, at here the surface area is too big, so that's why we consider the V here becomes 0. Okay, and then P2 here we also can consider the P2 is equals to 0 because it is also exposed to atmosphere. Okay, so therefore at the end, okay, we can simplify this equation in which that our HL is actually equals to Z1 minus Z2 minus V2 to the power of 2 divided by 2G. Okay, so this is actually our final equation. So from previous slide, we already know that the final equation that we can use to calculate the HL is based on this equation, okay, which is I label it as the HL, okay, and it is known as equation 1, okay. So let's solve one by one. So Z1 minus Z2. So the information about Z1 minus Z2, we can get it directly from the question in which that Z1 minus Z2 is actually 12 plus with 13, which is equals to 25 feet. Okay. And for this term, we need to get the V2. Okay, remember that we don't have the V2. But we can calculate the V2 value, okay, since that we already knew about the Q2, okay. So V2 is actually equals to Q2 divided by A2, okay. So from the question, it's given that this Q2 is actually is actually 1.2 feet cube per second. Okay, so we can multiply or divide by area, in which that the area in this case is 0.0491, okay, feet to the power of 2. Okay, so therefore our V2 is actually 24.4 feet per second. Okay, so this is our V2. So we substitute this V2 value into this equation and solve it. Okay, and at the end we managed to get our HL. So in this case, the HL value is actually 15.75 feet. Okay. So this is our final answer. Our HL equals to 15.75 feet. Okay, that's it. Okay, so as usual, we will list down all the information provided, including the one which is provided in the diagram, and we also gonna plan our formula. Okay, how can we solve the formula? Okay, so this is the diagram provided. Okay, and apart from this, we also have the information about the flow rate, okay, which is the flow rate at QA is equals to 0.014 meter cube per second. Okay, and then we also have the information about the HL, the losses, okay, in pipe, which is the value is 1.86. Okay, and for the formula, we know that we're going to use this equation. Okay, so let's check it out. What is the information which is already provided from the diagram? Okay, so before that, I will uh, check on this. Okay, so for example, the PA, so PA here is already given here. Okay, so PA is provided, and also the PB, which is 296 here. Okay, and ZA and ZB. Okay, so if you notice here, point B is higher than point A, so that's mean, okay, the ZB minus ZA is equals to 1 meter. Okay, so we can settle the ZA and ZB term. Okay, and about the HL is already provided from the question, which is 1.86. Okay, and in this case we don't have the HR, okay, because there's no motor in this case. Okay, and we need to find the HA from the question. Okay, what about VA and VB? For VA and VB, okay, we can calculate this formula based on the continuity equation. We know that from the continuity equation, we assume that the flow rate won't change. That means the QA will be equals to QB. Okay, so in order to calculate the QA and QB, which is A at A, area at A times the VA. Okay, and same goes to the QB, which is area at B times with VB. Okay, so we do have the QA. Okay, so for area at A and area at B, actually we can determine it from table. Okay, which is for area at A, okay, the spec for the pipe here is given here, which is it is a 3-inch schedule 40. For area at B, okay, it is can be determined from the table by referring at 2-inch schedule 40. Okay, that means we have to refer to the table in order to get the area based on the spec given. Okay. Okay, this is the table that we should use to determine the area for A and area for B. Okay, so we know that for the AA, okay, the spec which is given from the question for AA is actually 3 in schedule 40. Okay, and for AB is actually 2-inch schedule 40. Okay, so we know that the AA is 3-inch and the AB is 2-inch. Okay, so this is the call number, the nominal pipe size. Okay, so we want to know at this particular size what will be the flow area. Okay, so since most of the information that we have before it is in SI unit, so our value of the flow area should be in SI unit, which is we are looking for the value of area at this column. Okay, so let's try with the area at A, point A, which is 3-inch. Okay, so at 3-inch, okay, the flow area is supposed to be 4.768 times 10 to the power of -3. This is for AA. Okay. Meanwhile, for area at B, which is using the 2-inch schedule 40, which is this one, 2. Okay. So the area is 2.168 times 10 to the power of -3. This is our AB. Okay, so we will use this AA and AB value in order to calculate the VA and VB value by using continuity equation QA equals to QB, which is VA times AA equals to VB times AB. Okay, and then we know that the QA is already provided from the question. Okay. Okay, so from previous slide, okay, we know that this is the equation that we're going to use, which is the general energy equation. Okay, and since that the target, the question asks you to determine the HA, so we can rewrite this equation into this form. Okay, so we will find the each of the item consists in this formula. Okay, so for example, for VB, we can calculate it based on the continuity equation, which as I mentioned in the slide before, since that we already have the AB and also the AA from the table in the previous slide. Okay, and then the QA and QB is also provided from the question. Okay, so finally we can calculate the VB and VA. Okay, and then for the ZB minus ZA, okay, this one is actually the depth is between the point B and point A. Okay, so from the question, the ZB minus ZA is supposed to be 1 meter. Okay, and PB minus PA divided by specific weight. Okay, so this one is actually specific weight for oil. So we can determine it based on this equation. Okay, in which that the specific gravity of the oil, which is 0.86, okay, multiply with the specific weight of the water, which is at 9.81 kilonewton. Okay, so when you multiply between the specific gravity of the oil and multiply with the specific weight of the water, so you will get that 8.44. Okay, and of course the PB and PA is provided from the question. Okay, so as you know that the PB is 296 kilopascal, and we need to minus with the PA, which is the value is negative 28. Okay, so if we segregate the item like provided in separate item, like this is item 1 and this is item 2 and this item 3. Okay, so that it will be easier for you to check if there's any error in your calculation. So for item 1, if you substitute all the value, and you will get that the item 1 is 38.4. Okay, plus with item number 2, which is 1 meter. Okay, and then oh yeah, I forget that there's another item here, which is the HL, which is minus HL. Okay, so the value of minus HL is actually can be get from the question, because the question provides us the value of HL. Okay, so since that it is minus, so minus HL. Okay, so let's continue back. So this will be item number 4. Okay, so item number 2, let's continue. The item number 1 is 38.4. Item number 2 is 1, which is ZB minus ZA, and then plus with item number 3, which is equals to 1.69, and then minus with item number 4, which is the HL. Okay, so the HL in this case is actually 1.86. Sorry, it's not supposed to be negative because I moved to the other side, so that will be positive here. Okay, so it's supposed to be positive here. Okay, so if you calculate it all, okay, so it become 42.9 meter. So this is the answer for our HA. Okay, so I repeat again. Since that we already know that we have to use this equation, okay, and then we need to determine the HA. So we rearrange the equation in order to make that this is the value that we want to determine. So we move it to the left side, okay, and all the items we rearrange back, okay. So it's become plus HL here, okay. And then we calculate one by one, okay. And at the end, you get the HA value, which is equals to 42.9 meter. Okay, that's it.